Good afternoon, everybody. So the last presentation of this tutorial. First of all, thank you for the invitation, organizing committee. It's such an honor to present here after Paulo Sedeguin, Davi Chiaramonte. My name is Marcos Watanabe. I work in CTBE in the division of process intelligence. Today, I'll talk a little bit more about simulation and some results on the techno-economics, environmental, and also social analysis of biorefineries. Well, this tutorial outline is divided in 4 main topics. First of all, I'll introduce you the concept of virtual sugarcane biorefinery we developed in CTB. And then second, the third and fourth topics will be more focused on the results on the economics, environmental, and social studies. Okay, so talking a little bit about the place we come from. This is a picture that illustrates the Brazilian Center for Research in Energy and Materials. We're located in Campinas. There are 4 main national laboratories. We are in CTB, which is the Brazilian Bioethanol Science and Technology Lab. We also have the Synchrotron Bioscience and Nanotechnology Laboratory. And at the top left, we can see the 5th project, which is the Sirius 4th generation synchrotron slide source, which is, I think, the biggest project of Brazilian science and technology, about a billion reais of investment. In CTB, we are actually developing at the Division of Process Intelligence a tool, which is a framework we name Virtual Sugarcane Biorefinery. We basically depend on an integration of models that describe biofuel production and bioproduct production since the beginning, from the biomass and then its conversion and use. We also try to anticipate the impacts on the environment, on the economics and social aspects, on process and modeling. We are actually trying to anticipate before the technology is deployed. So what we have is basically a set of models represented here in the center. At the top, we can see, for example, the set of agricultural operations that are modeled since the pre-planting operations to the sugarcane harvesting, for example, and transporting. And a different thing is that we also integrate the simulation with the industry process. We basically depend on modeling on commercial software, Aspen Plus, so we can simulate the unit operations step by step. And also with Canasoft outputs that generate the agricultural model, then the outputs of Canasoft, Aspen Plus, and the usage model provide inputs to the group of 3 assessments we have. On the economic analysis, we depend on the economic engineering spreadsheets, and when we talk about social analysis, for example, we depend on a macroeconomics-based tool, which is the input-output matrix or input-output analysis. And the environmental assessment is performed using CIMAPRO software. So we have then quantitative subside to policymakers or even private companies, for example. This figure, this image illustrates how we work in the division. Basically, we depend on a team that is divided in 3 main focuses. First, biomass production simulation, and then industrial process simulation, with a team of 4 or 5 people, and the estimation on the investment. All of the analyses are interconnected, and then we provide inputs to the last step, which is the analysis itself for economic, environmental, and social. As I said, we can develop studies both for private interest companies or maybe public interest. For example, at the private side, we can assess a new bioproduct or a new biomass, for example, energy cane, let's say, or maybe for the public side, we can assess, for example, the impact of a new technology or a governmental program on the, for example, on the cost of product for the country, or maybe the effect on the economic activity of sectors. When we talk about bioproducts, for sure, we have to understand that having a model that is very accurate about the agricultural side is very important, because as we know, by simulating properly the costs of biomass and then calculate the industrial costs, currently about 60% of the ethanol cost is sugarcane, is in the agricultural side. And that's why we depend so much on the model of agricultural model. We can say that today we have 100 of parameters in Canasoft. We can vary, for example, parameters such as productivity, milling capacity by the industrial side, or maybe even vary parameters describing machinery. For example, the harvester speed that will impact on the ethanol cost, for instance. This is a picture that illustrates, I know it's a little bit small, but okay. We have here a representation of the cost breakdown of Canasoft model. The data are a little bit outdated, but it's okay. It's just to represent the kind of cost breakdown we have. We can describe, for example, costs of specific agricultural operations, the expenditures with chemical inputs, for example, expenditure with transportation costs, then a little bit more detailed analysis, for example, saying how much I spend with trucks, diesel consumption, labor, tire consumption, lubricant use, and so on. Also, other steps that impact a lot the sugarcane costs are steps such as vinasse application costs. Vinasse is a byproduct we obtain from fermentation, and we have to dispose it somewhere, and we place it in the field mostly. Also, we can, for example, estimate costs with irrigation, land, and taxes, and so on. Moving forward to the industrial modeling simulation, we can say that today we have simulated a lot of different technological routes. Basically, we focus mostly on first and second generation ethanol and bioelectricity, also because of the United Nations project Sucre in CTV. But for sure, as I said, we can include assessments of other kinds of biomass, such for example, energy cane, or maybe the impact of straw removal on the ethanol cost, for example, and other products such as butanol or maybe jet fuel and so on. And as I said, we use process simulation using commercial software like Aspen Plus, but we also developed capabilities on open source platforms such as EMSO. This slide depicts a print screen of Aspen simulation. Basically, we have a set and a group of unit operations, for example, of a mill producing sugar and ethanol and also steam and electricity. Basically, the level of detail of each box can be, we can go to the subsystem as much as we have detailed information to detail it. But the thing is that from this kind of simulation, we obtain the energy and mass balances that we'll use in our, for example, economic simulations. So from the mass balances, we know how much ethanol, how much electricity or sugar we produce, and then we can estimate, for example, revenues we're going to have in our cash flow analysis. Talking a little bit more about the methodologies, the first one is basically the engineering economics principles. We have the cash flow analysis, basically, which says the different technologies, and to do so, we depend on a lot of databases. And we can say that in the red box we have that Aspen simulations where mass balances, energy, and the main products can be used to estimate, for example, the investment we have in our industrial plant. So we cross this data from Aspen, and then we can obtain, based on capacity, for example, how much I would invest in the group of equipment. Here in the bottom, in order to estimate the revenue, we need to have a reliable base of ethanol, sugar, and electricity prices, considering that our cash flow analysis depend on analysis of, for example, 25 years period. We need to estimate historical prices for products, and this is a very sensitive part of any economic analysis. Basically, what we do is to estimate the price of a given commodity over a decade. In order to calculate the operating cost or the OPEX, as I said, we have a very reliable value for biomass costs. We estimate on Canasoft. However, we need to have other kind of cost database for example, chemical inputs, maintenance, labor, other utilities we use. So then, over the years, we have developed this kind of database that we can complement the analysis and then obtaining the total operating expenditures. And the result of the cash flow analysis basically represented in this green box. The main outputs are the internal rate of return, net present value, payback time, and production costs. Talking a little bit more about the environmental analysis, we can divide this picture in two sides, the top and the down. First, for those who doesn't know this kind of assessment, basically we can simulate, for example, the inventory, which means the materials and all the energy used through the whole process, since resources extraction, passing through input manufacturing, inputs transportation, biomass production, and then we transport it, convert it into a product, and then we distribute it, for example, ethanol, and then we finally use this product in fuel engines, for example. So, to give an example, for example, for sugarcane production, we need to estimate how much oil and gas we need to use to produce, for example, inputs like fertilizer, and then how much energy, how much materials we spend to transport this fertilizer to the field, and all the materials we have to use to transport the sugarcane that is finally produced to the mill, and all of the material we have and energy we have to spend in order to distribute it and finally use it. So, in possession of this entire inventory, we can finally calculate the impact categories. Here we just present a few, but depending on the method, we can have, for example, 14 categories. Here we can split in global and local impacts. And why? Because global impacts, you cannot track it geographically speaking. For example, the most famous one is the global warming potential. So once you burn your fuel in your engine, you cannot track where the CO2 is actually. The same for the energy use because you are depleting the entire fossil fuel reservoirs over the world. On the other hand, we can also calculate quantitatively some local impacts like human toxicity, land use, or eutrophication, for example. It is local because we can track it geographically. For example, fertilizer use will increase eutrophication in a specific region, for example, a farm. And finally, the social life cycle assessment and the social analysis is usually neglected from the sustainability assessments, maybe because it's very difficult to obtain quantitative metrics to assess the impacts of some, for example, biofuel technology over the whole entire production chain. And in CTB, we can actually do this. We depend on the concepts of social life cycle assessment, which is very, very close to the environmental life cycle assessment, because we depend on inventory, which means that we need to track every step of the production chain in order to understand the impact on the stakeholders. And how we do it? We need to have an input-output database and then track, for example, the impact of ethanol production over the entire supply chain. For example, what is the impact on workers, not only from sugarcane field, but also from fertilizer industry and also diesel industry. Every input that is used in the biofuel production, we have to measure their impacts on given stakeholder category. In quantitative terms, we can say that we have mainly 5 indicators: the jobs we create over the supply chain, the total occupational accidents, then the wage, education, and gender profile of workers. And I'll present in the next slides some examples of such analysis. Going straight to the second part of this presentation, some examples of techno-economic studies. When we talk about techno-economics, we have to keep in mind that for the investor, the decision making can be divided into options. First one is to save his or her money in a safe investment or a bank account, or maybe invest in a project. Let's say that he likes the biorefinery and the biofuel industry. So he'll try to assess quantitatively if this is worth or not. So thinking cash flow analysis, we separated 3 main indicators here. The investor can select based on a variety of project options for A or B or maybe C or N projects. And basically, he has to observe some basic concepts. First one, the net present value, the NPV. What does it mean? It means how much money I'll make with this project. So let's say that the net present value of a project is 100 million reais. The net present value has to be positive, always. And for example, 100 million reais means that a given company will add 100 million value to its company. So it's interesting, for example, to have this project added to the options of the company because it's positive and it's higher when compared to the other options. A second parameter of comparison is the internal rate of return. It comes from the same cash flow, but the matrix is a little bit different. It says in a percentage per year, what is the rate I can earn in terms of monetary gains. For example, let's say we have a project with 20% per year rate of return. In the sugarcane industry, a good parameter is the famous 12%. Every rate, in Brazil at least, every rate above 12% per year, discounted from inflation, which means a real rate, means that you have a good potential of earning money. So if you have a project with a rate above 12%, then the net present value will be positive at the same time. It's the basic concept. And the third one is the payback period, which is, I think, the easiest one to understand because the payback time is the time the investor have to wait in order to recover his investment. So the fastest, the better. In CTBE, for sugarcane industry, we use some basic concepts in every assessment. For example, we assume that the model is vertically integrated, which means that the owner has the control over the farm and also over the industry, which means that basically the biomass production cost is exactly the cost we're going to assume in the industrial step. The discount rate, I already told you, is the minimum acceptable rate of return of 12% per year, which is a real rate, which means that inflation has already been discounted. Project lifetime is around 20 to 25 years. Depreciation is 10% per year, which means that all the equipment and buildings will be completely depreciated, at least by accounting terms, in 10 years. In Brazil, we have a 34% income tax rate, which the money we have to return to the government. And prices, as I told you, we need to have a reliable database, and then we estimate an average for a decade. And depending on the database of the study, we have to update it using the proper inflation index. In Brazil, we use, not in Brazil, in CTBE, we use the IPCA, which is the Consumer Price Index. In order to finish the cash flow analysis, we have to keep in mind that we need 3 main inputs. The first one is this arrow, straight to the down position, pointing to the bottom. It represents the investment we have to make in buildings, equipment, and so on. Cash flow analysis also depend on the operating expenditures. So in the virtual sugarcane biorefinery, we have a good database to estimate, for example, as I said, the expenditures we have with labor and chemical inputs we spend every year to produce, for example, ethanol. And the third and last element is the revenue side. So we have to estimate how much ethanol or how much electricity we produce over the year, and then we cross this data with the price data, and then we obtain a projection for revenues over the 25-year period. This is already a real example of assessment of scenarios. Some of the assumptions I already told you in the last slides. Basically, what we have here it's a comparison between first generation mill against an integrated plant producing both first generation and second generation. Project lifetime here, discount rates the same, depreciation. At that time, in July 2014, prices were 1.34 to the anhydrous ethanol, and for electricity, 132. Only to update these values, for now we consider something about 170 reais per liter of anhydrous ethanol, and to electricity a value around 200 reais per megawatt hour of electricity. Before presenting the economic results, we have to understand that the cash flow analysis depends on the technology description. Here we have description of 4 main scenarios. The left side of the table represents the first generation scenarios, and the right side the integrated first and second generation. Here we're comparing a lot of effects. For example, the effects of scale in the first generation ethanol production. First generation base represents kind of outdated technology. One first generation advanced represent a mill which has twice the scale of 1G base. Also, we're recovering straw from the field. We fixed a value of 50% using the Bay technology. So the ethanol production is twice as much because of the capacity of the plant. Also, we can produce surplus electricity. This value is very high because of the straw removal from the field. In considering the second generation plants integrated to first generation, we basically have the same technology for first generation, which is the 1G advanced. On the other hand, we have different amounts of second generation or cellulosic ethanol production in the current period. From 88 million liters of second generation ethanol, we can move to 158 million liters in a future technology. And how we can get this? Basically, our assumptions on technology changes. We have improvements. For example, when we compare current and future technologies, we see that steam explosion residence time and also enzymatic hydrolysis residence time decreases from 15 to 5 minutes. Enzymatic hydrolysis residence time reduces from 48 to 36 hours. Also, some industrial conversions. Oh, sorry, I'm having trouble here. Scratch, it's okay. So when we observe the industrial conversions, for example, from cellulose to glucose and xylene to xylose, or for example, C5 sugars converted to ethanol, we see that we have increases in these yields. So the result is that we have, for example, for first generation scenarios, we compare the investment we need to make in the plant. For sure, we need to invest a lot in order to obtain a plant crushing 4 million tons of sugarcane per year. But let's see the results itself. So the net present value increases when we compare first generation base to advanced, mostly because of scale, the scale effect, and also because the electricity surplus that we obtain from recovering straw from the field. The same results observed in terms of internal rate of return. the value we obtain to the advanced scenario is 14.1%. On the other hand, for more outdated technologies, this returns a little bit lower. Obrigado, professor. Obrigado, Bruno. The payback period is discounted one, is not as simple. So we apply discount rate on the cash flow, and that's why this value is so high. It decreases from 17 to about 14 years. In order to return the investment, you have the investor had to make. And when we move to the comparison between second generation technologies, we can see that investment is pretty much the same. On the other hand, we have really different net present values. Of course, the improved technology we expect to have in the future will benefit a lot investors if there's a technology learning curve and policy making that will bring a new situation to the sugarcane sector, of course. But this is an exercise of how it would be in the future if these improvements were actually observed and implemented. An interesting is that currently, if we compare second generation technology with first generation technology, we can say that we are not there yet in terms of cellulosic ethanol, basically because of the low yields and some trouble we have still in the pretreatment and hydrolysis technologies that are facing the beginning of its learning curve. But in the future, maybe we'll get internal rates of return close to 18.5% in the future and a discounted payback of about 8 years. The next slides will be a presentation of some results of a study that CTB developed with BNDES, which is the Brazilian Bank for Development. In this study, the main objective was to compare first and second generation ethanol production costs over time, how it would behave if some public policies were implemented, and what would happen if some technology development would actually be implemented over 15 years. So we basically divide in 3 main periods: short, medium, and long term, from 2016 to 2030. And the difference among the scenarios are in the assumptions, for sure. Okay, we have the base case that represent the current situation of some mills in Brazil. But in the blue boxes, we have the first generation scenarios and how would they evolve over time from short to long term. Basically, what we have is that we're always producing ethanol and electricity. The difference is that the biomass we use, we're gradually introducing new biomass, like we're trying to recover straw from the field in the medium term, and also in the off season we would use energy cane as an additional biomass. In the long term, we also would have energy cane during season and off season period. When we talk about how we use the byproducts of mill, we can see that gradually biodigestion is introduced in the first generation plants, and then with biogas we could substitute inputs like diesel and produce more electricity to the mill that would help the investor to have a faster payback. And when we look at the energy efficiency, we can see that one first generation steam consumption will gradually decrease from 380 kilograms of steam per ton of cane that is crushed to 360. And for the second generation, we have a lot of assumptions in, like I already presented to you, in terms of industrial conversion and industrial parameters, but here I'm only highlighting how standalone plants, the 2G plants, which is the plant that's isolated, with integrated first and second generation plants, we can see that the difference over the short, medium, and long terms It's, of course, the increase on second generation yields in the industry, but also the use of biomass will impact a lot, mainly the integrated scenarios, because of the introduction of energy cane. Here's an illustration of the 14 scenarios we assessed in this study. You don't have to memorize it, but basically this set of scenarios are related to the first generation scenarios for the short, medium, long term, for the integrated scenarios, short, medium, long term, and the standalone plants. The difference between A and B is the presence or not of co-fermentation. We see that B scenarios are related to scenarios in which C6 and C5 are fermented together. So the assumptions are really similar to the other table I presented in previous slides. The reference date for these results is July 2014. At that time, the exchange rate was 2.30, which is pretty low for our current situation. Another important assumption is how the enzyme cost would decrease over time, decreasing from 13 cents of dollar per liter of second generation ethanol to 6 cents per liter of second generation because of economies of scale in the manufacturers, mainly the enzyme manufacturers that would expand the number of mills over the country, and the clusters would be more mature, and then that would make this reduction possible. This table is very dense as well, but basically what you have to see is that as much as if we evolve, the scenarios evolve over time, we see an evolution, the investment on both first and second generation ethanol, but as much as the technology evolves, the investment per liter of ethanol decreases because of the higher yields on, especially on the second generation plants. An important is our assumption is the ethanol production cost approach we used. We have integrated, as I said, integrated scenarios that produce both first and second generation ethanol. On the other hand, we need to know the second generation cost isolated from the first generation. So in order to do so, we have this approach. Of course, I can simulate the cost of this integrated ethanol, and in order to obtain the second generation ethanol, we do the following approach. We have to have a kind of mirror scenario that depicts the situation of a first generation plant exactly like this first generation plant here. So how we split the costs? Basically, we have an approach that is based on revenues. So if first generation ethanol contributes with 80% of the total revenues of the mill, then the first generation ethanol will absorb 80% of the costs. So I can absorb 80% of the biomass cost, 80% of capital costs, and so on. Then we can obtain the cost per liter just dividing these yearly values by the total amount of liters produced. I do the same approach to the integrated scenario, and then the only unknown is the second generation ethanol cost. It's nothing more than a weighted average, which says that the cost of integrated ethanol is the weighted average between the participation on volume produced of first and second generation ethanol produced times its cost. This is an example of the result we got in this study. At that time, first generation ethanol had a cost of about 1.16 reais per liter. Only to have an updated value for now, we have for first generation something about 1.50 and 1.60 reais per liter of 1G ethanol. Then when we use this formula or this expression to separate second generation cost, we can see that we can see a higher cost actually. So when we compare 1.52 at that time with 1.16, we can see that second generation did not has a lot to learn with the first generation technology yet. And then as I said, the integrated ethanol cost is the weighted average of 1.16 and 1.52 times their participation. This table depicts how is the difference between first and second generation ethanol over time from the short to the long-term scenarios. This is clearer when I show this picture. Basically, we have the red and blue lines here. We can see the second generation cost decreasing over time. Basically, we start from a point that is 1.50 something per liter, and then we can get, in the long term, something about close to 60 or 50 reais per liter, of course, reference date of 2014. And first generation ethanol, that in the short term had a lower cost, can reduce its cost as well because of the introduction of new technologies in the field and also the introduction of energy cane. And then we can see, but in the medium term, we notice that there's a change. If public policies to foster second generation ethanol development and actually developments in the private sector were really implemented, then this would be possible. So when we look at the cost breakdown of just second generation cost, we can see that mainly we depend still on the investment. So the capital cost, which means pretreatment and hydrolysis, represents the major part of second generation cost in Brazil. The second contribution comes, of course, from biomass and then enzymes, and also expenditures with maintenance, which depends on the investment. So that's why maintenance is so high in second generation ethanol. So we can see that if capital, enzyme, and biomass costs actually reduce over time, we can see that capital costs will be dramatically reduced, also biomass and enzyme, and that scenario will make possible the situation where second generation is more attractive than first generation. Even performing some sensitivity analysis for biomass in the left side and enzyme, we see that in the red results, we can see second generation cost. It would vary from 1.50 to 1.60 and 1.40, and first generation. And the medium term, there's an overlap. So considering uncertainties, we cannot affirm that second generation would be more attractive, but there's a large potential for this. And the long term, that would occur if we consider biomass as the parameter of sensitivity. The same analysis was performed looking at enzyme cost. For sure, for first generation facilities, there's no sense of doing this, so that's why the value is also steady. Then we can see that considering only the uncertainties on enzyme costs, then at the medium term, second generation cost would be more attractive than first generation. And of course, in the long term, that would be even more clear. And the most important part is the investment, because as I told you, is the major contributor to the second generation cost. If we put a variation of 30% on the capex, we can see similar results. For second generation, we have a larger uncertainty in the beginning because investment is the major component of second generation cost. On the other hand, as much as we advance in the time, this uncertainty decreases because investment is not so important as it was in the beginning. And then we can say that second generation is finally competitive with first generation ethanol. Talking a little bit about competitiveness with gasoline and oil prices. We know that we have, over the last 5 years, something like this in the behavior of the price of crude oil. It was steady around $100 per barrel. However, by the end of 2014, we had this kind of huge decrease, and we reached some figures around $60–100 per barrel, and currently we can say that oil price around 50, and that's not so good for biofuel. So we had this exercise in this study. For example, we know that at the short term, ethanol, second generation ethanol would cost around 1.53 reais per liter. And that's equivalent to say that if I produce a gasoline using WTI crude oil, then second generation would be competitive in a situation by which crude oil should cost $128 per barrel, which is a lot, and I don't know if this can happen again. Maybe in the future, I don't know. Nobody knows actually. In the future scenario, as after the end of the second generation learning curve, if we obtained a cost of second generation around 50 reais per liter, of course for the reference date of 2014, then that would be equivalent to say that my second generation ethanol would be competitive even in a scenario of $44 per barrel oil price, which is good, which is actually the figures we notice right now. The third part is the assessment of the same scenarios, but considering the environmental impacts. Again, the same 14 scenarios of integrated second generation and standalone second generation and first generation facilities. Here we also have a very complex table, but it's okay. The important thing is that the ethanol yields increase over time for first generation scenarios, integrated scenarios, and also to the standalone scenarios. And electricity output varies a lot depending on the technology, but stays around 70 kilowatt-hour per ton of sugarcane. So focusing on the GWP impacts, here you have a comparison of both short-term results and also integrated scenarios over time. So at the left side of the chart, you can see that most of the impacts are caused by the agriculture step, of course, mainly because of fertilizer and diesel production. We can see that the global warming potential decreases from 25, let's say, grams of CO2 equivalent per megajoule of ethanol to a value of around 12 grams of equivalent of CO2 per megajoule. And this is possible because of the reductions of impacts on the biomass production step. When we look at the integrated scenarios, the same behavior is expected. We would decrease the emissions per megajoule of ethanol from a magnitude of 20 to a magnitude of 12 in the long term. If we consider the economic-based allocation, and what is the economic-based allocation? When we calculate the environmental impacts, if you produce more than one product, for example, if you produce ethanol and electricity, you have to split the impacts between ethanol and electricity. And if you decide to make this decision based on the economic allocation procedure, then this would be very similar to the production cost approach. So basically, if ethanol contributes with 80% of revenues, then it would pay for 80% of the impacts. What we see here is that for the scenarios 1, 4, and 7, we're highlighting this yellow bar. That's very interesting. What is the yellow bar? The yellow bar is the second generation emission in a standalone facility. When we compare this emission with an integrated ethanol, which is this emission here, about 20 something, we see that apparently the standalone facility ethanol is better. But this happens because the bagasse and the lignocellulosic material that comes in the standalone facility that is purchasing this material, this impact from biomass have already been paid by a first generation facility somewhere in the country. So that's why apparently we have second generation ethanol producing less impact when compared to the integrated scenarios. However, if you consider another allocation procedure, for example, energy-based allocation, we see that the same yellow bars, what we see is that the second generation from a standalone facility increases, it impacts from 12 or something to 20. In why? It's because the bagasse and lignocellulosic material has a very high energy density. And if you have an energy allocation criteria, the product that delivers more energy will pay the most for the impacts. And that's why when we compare, for example, the emissions of the second generation ethanol, even with an integrated ethanol, the impacts are very similar just because I changed the economic to the energy-based allocation. And qualitatively, we see that impacts decrease over time as much as we evolve in the second generation technology. Here is, I think, is the last chart that depicts the impact of 2G ethanol. This represents the CO2 equivalent emissions that I can avoid with 1 hectare of sugarcane, or depending on the scenario, the energy cane. As we see, if we have in this scenario, number 1, by having 1 hectare of sugarcane, we can avoid about 11 tons of CO2 per hectare just by, if I consider that I'm substituting, the ethanol is substituting gasoline, C gasoline, and that electricity output is substituting the average electricity we have in Brazil. So that's the result. And when we, an interesting point is that when you compare scenarios 1 and 4, the main difference is that scenario 4 produces electricity in the same area, and in scenario 1 produces only ethanol. So we can see that, this scenario 4 produces more ethanol than scenario 1. And that's why an interesting point is that if you have a scenario producing more ethanol than electricity, this would be more interesting in terms of impacts avoided for the same hectare of sugarcane. And qualitatively, we can see at the long term substitution of grid electricity, the average grid electricity, but by bioelectricity, and substitution of gasoline by second generation ethanol would avoid something about 45 tons of CO2 for just 1 hectare, and this is possible because of energy cane. And the last part of the presentation will focus on some results of social studies. The social assessment, as I said, is usually neglected, but the social impact is very important. We can define social impact like being positive or negative, depending on the impact it has on the stakeholders. It also influences the access to markets. So many initiatives like Bom Sucro and Roundtable of Sustainable Biomaterials take social metrics into account. And what is the methodology exactly we use in the virtual sugarcane biorefinery? We basically depending on social life cycle assessment and input-output analysis. Then we can calculate both the local and effects over the entire supply chain. And I will present to you in this afternoon only the impacts we have on the workers. Basically, we can simulate the agricultural and industrial phases using our softwares. For example, we can vary agricultural parameters in agricultural operations, for example. And this will influence the jobs we create in the agricultural side. We can also calculate in the average wage using the same model. In the industrial phase, we have an equivalent model to calculate jobs and average wage, but varying industrial parameters and also the technology. So we can calculate local impacts in the mill. And then we can cross these results from our softwares with official databases. For example, database from Ministry of Social Security, and then get the occupational accidents. we would expect from that difference in agricultural and industrial scenarios. For those who doesn't know input-output analysis yet, for example, let's imagine you need to produce ethanol and you need a biorefinery. In order to produce ethanol, you need inputs: sugarcane, chemical inputs, maintenance, transportation services, a lot of services and goods. Then, for example, sugarcane depends on a lot of other industries. For example, we depend on oil and gas industry, we depend on rubber industry. For example, packing industries depend on, for example, forestry services. So there are a lot of impacts that are actually infinite rounds over the economy, but this equation can be solved by calculating the direct and indirect effects. So basically what we have, that the direct effects are those economic efforts made in the first round of input suppliers. For example, sugarcane is a direct effect, and indirect effects are all of the industries that provide inputs to the input suppliers to ethanol production. So this rounds of sectors is complex, and this system can be solved by using this equation. Basically, what we have is we don't know the impacts over the economy, which is the x. The x is a vector of direct and indirect impacts over the sectors. So it's a group of sectors. And in order to calculate this unknown variable, we need to simulate a shock or a change in the final demand of a product of interest, let's say ethanol. And we also depend on the Leontief inverse matrix, which is basically an identity matrix minus a table, which is the table of direct requirements. This table is obtained in the official database from the government, like the IBGE database. And what we get is that input-output analysis is actually is generating an inventory of industries we are activating when we need to produce ethanol. So if in possession of this inventory, we of course calculate the economic outputs over all the industry. For example, if I produce 1 billion reais or $1 billion of ethanol, I need, for example, $300 million of sugarcane, let's say, or $100 million of chemicals and so on. And we can capture even in the indirect effects. So effects we are not expecting. For example, coffee industry is activated when you produce ethanol. So we can calculate the value added over this production chain, the impact on GDP, and also we can cross these monetary outputs with social database. Then we can calculate jobs we created over the country, and also track the wage, education, and occupational accidents profile of the workers involved in all sectors, not only sugarcane and in the mill. And a third use of this input-output analysis is the environmental assessment itself. We can cross with the official database from the Ministry of Science and Technology, for example, and obtain the sectorial emissions or maybe the energy used by sector, and then make a ratio that by which we can convert economic into environmental impacts. So what's the step-by-step of the social analysis is here. You simulate, for example, I need to produce 1 billion reais or $1 billion of ethanol, then I know the sectors I'm gonna be disturbing in the economy, let's say like this, and each value we're gonna have to produce in order to attend this demand. Then we calculate the number of workers involved in the entire production chain. With official database like the annual report on social information or general database of unemployed and employed, we can estimate the number of accidents, the total jobs generated in the mill and the supply chain, and also indicators like average wage, education, and also gender. So we compared three main scenarios. 1G base, as I said to you, represents a first generation distillery producing only ethanol with relatively outdated technologies, like for example, sugarcane is burned in the field, the harvest is manual, and the planting is semi-mechanized. As we go through the 1G advanced scenario, we have mechanized harvest. We can produce first generation and electricity surplus by recovering straw, and represents a best current technology we have in Brazil. And the future scenario is the integrated first and second generation mill, which depends on also in a very similar agricultural scenario, but the difference is that we're producing second generation ethanol. So the result is, considering the input-output analysis, we can see that first generation with relatively outdated technology produces more jobs per liter of ethanol, and basically this happens because of the manual harvest, which depends on sugarcane cutters, and that's why the impact of direct jobs is higher than the indirect one. As much as we advance to more 1G and 1G, 2G technologies, we do not depend so much on workers from agricultural sector, but we introduce a different profile of economic sectors, like for example, workers from trade, workers from the services or transportation, and the profile of job creation changes. And of course, the expected number of workers per liter of ethanol decreases. But it decreases. On the other hand, the quality of job that is created is completely different. For example, if we look at the expected occupational accidents we expect from producing, for example, 1 million liters of ethanol, this is less than half of the impact caused on occupational accidents in the first generation base. And again, because of sugarcane cutters. If you have thousands of cutters here working and not so good work conditions, the probability of occupational accidents increase, and more than that, we'll have more workers employed, so the probability of obtaining accidents will be higher. So as we move to advanced scenarios, these impacts will be drastically reduced, which means that second generation and first generation advanced are good for considering worker quality, worker job quality. When we look to wage, the average wage in the entire supply chain and the education profile, we see that the annual wage in USD, considering the purchase parity, first generation base workers on average have lower wage when compared to the advanced scenarios, for example, second generation scenarios. And this happens because the profile of workers of the entire supply chain changed. We're not talking about more an agricultural based product, but I'm talking about a product that has a different signature. It depends more on transformation and service industries, and that's why they are better paid. Then we expect better average wages. The same occurs to education. The average education for a worker in the outdated mill and supply chain would be around 7 years, and it can increase to 8 or 9 years when we consider this different profile of workers. Just taking a look on the wage profile, the blue line and the black lines are actually here are the same, because there's no so much difference between the supply chains. And the 1G base is the orange dotted line. What we see is that the number of minimum wages of the average worker moves slightly to the right, which means that the expected wage of worker of these advanced supply chains are a little bit better because of this slight change here. Basically, and when you consider outdated technologies, the average wage is around 1 to 1.5 minimum wages. This is more clear when talking about education profile. For example, the sugarcane cutter is contributing the most for this result of the orange line because 1G base depends on the agricultural worker. What we see is that basically sugarcane cutter has an incomplete elementary school. As much as we move to advanced technologies, we have a different profile of worker, and then it will be more likely that we find a worker in the supply chain with, for example, a complete high school. So we can see that these lines are moving to the right. So that's good when considering advanced technologies. And so to finish this presentation, our conclusions is that this is possible because of the input-output analysis that makes these quantitative results possible, and to compare different technological scenarios. We can capture both direct and indirect effects over the entire supply chain. That's really, really good when we consider the life cycle approach. We can see that outdated technologies provide more jobs. On the other hand, these jobs don't have good quality, and so as much as we move to first generation advanced and integrated first and second generation, we expect lower incidence of accidents and also better wages, higher education, and also more female participation in the supply chain. So that's all. Thank you.
Well, this completes our tutorial session. I hope you have enjoyed as much as I did. I learned a lot from Professor Chiaramonte and Dr. Watanabe, which I deeply thank you very much for your kindness and showing your knowledge, especially to me. Okay, so I also hope you enjoy the conference during the following days. And you should receive a copy of the presentations. I think you noticed that all the three of us, had more slides to present, which we skipped. The ones that I didn't show you are after the thank you slide. So if you have the time, please consult the complete set of slides. And well, I'm available and all of us, you're available for questions. Okay, so thank you very much. Have a nice week.